G'day and welcome to a special episode of Plugged in Australia, the podcast exploring electric vehicles and the future of transport here down under. Now usually we round up the latest news on models, pricing, policy, but today I wanted to do something different, a deep dive into some cutting edge research that's happening right here in Australia, and it could shape the EVs we'll be driving in the coming years. The paper we're unpacking is called Understanding Batteries Integration in EV Structure, Trade-offs and Optimization. It's been published in the Journal of Energy Storage. It's from a team at Deakin University's School of Engineering in Geelong, Victoria, led by researchers, now I apologise if I butcher your names, Umar Shafiq Awan, Kazem Kabri, Ali Zolgofaran, Sean Winfrey and Bernard Rolfe. These engineers took a close look at how to make the battery pack not just a heavy box bolted underneath the car, but an actual part of the vehicle's structure, like turning it into the spine or ribs of the chassis. Now, why does this matter for us Aussies? Our roads are tough, potholes in the city, long highways, rough regional tracks, and EVs that are already carrying big, heavy batteries. If we can make those batteries help strengthen the car while saving weight, we get better handling, longer range from the same size battery, we get smoother rides and potentially safer vehicles. Plus, lighter cars mean less energy used and lower emissions overall. This isn't sci-fi, it's practical engineering. It could influence the next generation of EVs that are hitting our shores. So I'll explain everything step by step. Not going to assume you're an engineer because I know I'm not. We'll cover what structural integration means, the two approaches the team tested, the impressive results for stiffness and vibration control, how they optimize for weight savings, and really what this could mean for future Australian EVs. Let's get into it. Okay, first let's set the scene. In today's EVs, the battery pack is usually a big, flat module attached to the floor with bolts. It's heavily protected, but is basically dead weight when it comes to helping the car hold itself together. The structure around it, the chassis or body, has to be designed to carry all the loads, bending from corners and bumps, twisting over uneven ground, and vibrations from the road that affect ride comfort and noise. The Deakin team asked, what if the battery itself became part of the structure? Think of it like using the battery as built-in reinforcement, similar to how carbon fibre or steel beams strengthen a building, without adding any extra parts. This idea isn't brand new. Some manufacturers are experimenting internally, but published research is rare. So this study fills a gap by quantifying the benefits and trade-offs. The advantages are clear. A stronger, stiffer structure means better handling. The car feels more planted on twisty roads or when loaded up for a family trip. It also improves what's called NVH, which is noise, vibration, and harshness. Without an engine rumbling, EVs are quiet, but road noise and vibrations that can still come through. A stiffer body reduces those, making the cabin smoother and more refined. And the holy grail? Weight savings. Batteries are heavy, often half a ton or more. If the pack helps carry loads, you might need less steel or aluminium elsewhere. And yes, I said aluminium, not aluminum. Cutting overall mass. Lighter car equals better efficiency equals longer range from the same battery, or the same range with a similar, cheaper battery. For Australia, where range anxiety still lingers on longer drives, it could really be a game changer, as much as I don't like that term. The team notes structural integration could reduce pack mass by up to 10% and in turn boost range by 14% in some cases, though it exposes batteries more to road vibrations, hence the need to study trade-offs carefully. The research used a simplified model based on real OEM electric crossovers body structure to test ideas without revealing proprietary details. They focused on bending modes, so how the car flexes up and down, and torsion modes, side to side twisting. and these are key for real-world performance. Alright, so the study was split into two phases. Phase 1 was the more conservative approach, so integrating the battery by adding H-shaped beam reinforcements around it to boost strength. So imagine the battery pack sitting on the floor and you weld or bond strong H-beams, like a steel I-beam but shaped in a H for efficiency, along the sides and underneath. Now this connects the battery more rigidly to the rest of the structure. Results were impressive right away. So compared to a base model without this integration, bending mode frequencies, so the natural bounce rate of the body, increased by 54%. Higher frequency means the structure resists flexing better under loads, like when hitting a pothole or cornering hard. Torsion modes, the twisting resistance, improved by up to 12%. Now, why does frequency matter? Lower frequencies can amplify vibrations at certain speeds, leading to boominess or harshness in the cabin. Higher ones push those issues out of the normal driving range, making the ride quieter and more comfortable. The team used finite element analysis, computer simulations of stresses and vibrations to measure this precisely. This phase shows even a moderate integration with added beams gives big gains in stiffness without completely redesigning the battery pack. It's a step manufacturers could take sooner. It's a balancing benefits with keeping some isolation from road shocks. Alright, so in phase 2, the team went bolder, fully integrating the battery by modifying the pack assembly itself to act as structural elements. No extra beams needed in some areas. The battery becomes load-bearing directly, with its casing and modules contributing to overall rigidity. Here, improvements jumped, so the bending mode frequencies up 102% over the base models, torsion up 36.6%. That's more than double the stiffness in bending. It's huge for handling and safety in crashes or for heavy loads. The structure vibrates at much higher rates, far from what you would feel on normal roads. But raw strength isn't everything. Cars can't be too heavy, so the team applied size optimization. So mathematically tweaking thickness and materials to minimize weight while keeping those frequency gains. For phase 1 level, they held bending at nearly 40% or higher and torsion 12.6% higher than base, saving about 75 kilograms in total. For phase 2, bending 62.5% higher, torsion 30% higher, with 87 kilograms saved compared to a non-optimized integration. 87 kilos is like removing a passenger plus maybe some luggage. It's significant for efficiency. Less weight means less energy to move the car, extending range, or allowing smaller batteries for the same distance, which then in turn will reduce weight even more. Optimization ensured no loss in key performance, proving you can have stiffness and lightness together. Now, what are the trade-offs? Full integration exposes batteries more to vibrations, potentially accelerating wear over time. And the team notes this needs further study on fatigue, but stiffness gains could outweigh risks with smart design. Alright, so let's pull it all together. What does Deakin's work mean for us? This research shows structural batteries aren't just theory. They can dramatically improve EV chassis without massive compromises, up to double the bending stiffness, over a third better torsion resistance, and nearly 90 kilograms weight savings through clever optimization, all from making the battery pull double duty. For Australian drivers, imagine EVs that handle our varied roads better. Less body flex on corrugated outback tracks, quieter cabins on highways, safer structures in accidents, so stiffer equals better energy absorption in some cases, and longer real-world range from lighter weight. With our push for efficiency under the new vehicle emission standards, this tech could help manufacturers meet targets while giving us better vehicles. The Deakin team have laid groundwork that could influence global decisions, but it's especially relevant here with our engineering talent and EV adoption growth. Future studies might look at crash safety of real-world fatigue, but this proves the potential is real. And that's our special deep dive into structural battery integration. Thanks to Deakin University team for pushing EV innovation forward. If this sparked thoughts on future tech or Aussie research, please let me know. Send me an email, info@pluggedinaustralia.com.au. Thanks again for joining this special of Plugged In Australia, and until the next time, stay plugged in, stay charged. Ci vediamo.